seminar series. Hello, welcome to the Shotton School of Engineering and the latest presentation in our seminar series in modern artificial intelligence. The series is aimed at unifying scientific communities around the influential research ideas of today that we predict will have a major impact tomorrow. And we hope that the discussions that result here will promote groundbreaking discoveries and contribute to building a better world. I'd like to thank Daniela Bankovakovic for her strong support, as well as my own Department of Electrical and Computer Engineering for hosting this series, which has evolved since its launch into a respected and significant event in the AI world. When I first conceived of the series, I hoped that I would be able to attract highly esteemed speakers doing revolutionary work in their respective fields. I've mentioned this before, and I will say it again with some humility. I have succeeded beyond my wildest dreams. Our guest today simply could not be a more perfect example. When Jamie Shotton was named one of the MIT Technology Review's top young innovators a decade ago, they headlined their story. He gives computers new ways to see the world. You must admit that's a pretty attention-grabbing. The game enthusiasts here will be excited to learn that the word being referred to led to the development of a motion sensor for the Xbox 360 console and later to the HoloLens. And I think it's fair to say that since he began his career, he's been doing attention-grabbing work. Jamie earned his PhD in computer vision from the University of Cambridge in 2007. And the following year, he joined Microsoft, where he began as principal researcher and head of the Machine Intelligence and Perception Group, and ultimately accepted the post of partner director of science. In 2021, he became chief scientist at Wayve, where he's now working to build foundation models for embodied intelligence, with the goal of enabling safe and adaptable autonomous vehicles. His honors include the Longest Higgins Prize, the Royal Academy of Engineers Gold Medal, Robert Award, and the IEEE Pattern Analysis and Machine Intelligence Young Research Award, among others too numerous to list. In 2021, he was elected a Fellow of the Royal Academy of Engineering. He's an absolute superstar in the realm of AI, where he has explored applications not just in gaming and autonomous driving, but in robotics, healthcare, and many other areas, and we are very lucky to have him with us today. His presentation is entitled Frontiers in Embodied AI for Autonomous Driving, and he is going to be discussing his work to unlock the potential of autonomous driving in complex and unstructured urban environments. Any of you who have had to navigate the streets of central London or Midtown Manhattan will be familiar with those kinds of environments. I know none of us can wait to hear from him. So without further ado, I give you Jamie Shotton.
Hello, good morning, and it's a great pleasure to be here. Thank you for the kind introduction, Anna, and the invitation to be here. And it's a pleasure to be back in New York and to talk a little bit about the work we're doing at Wayve. So, get the clicker working. Okay, no clicker today. So, the open road, the feeling of freedom as you drive with the panoramic vistas, the wind in your hair, the thrill of the pedal to the metal and the acceleration. Well, more generally, I think this is the picture that you see. The average driver in the US apparently spends about 50 hours a year stuck in traffic. That's over 2 full days of their lives gone to traffic. And wouldn't it be fantastic if you could spend that time productively instead, maybe reading a book, watching a movie, talking to your friends, playing with your kids? But more seriously than that, there's a huge toll we pay as a society for driving in the form of accidents, deaths and injuries. And the numbers here are really, you know, they're very sad, and there's you know, many more people. There's many people killed and many more people injured than killed each year on the roads. And sadly, the vast majority of this is down to human error, speeding, aggressive driving, chemical impairment, drowsy driving, etc. So there is a huge opportunity for technology, if it can be made safe and performant enough, to reduce this burden of driving. But beyond that, there's also huge economic incentives, and you know this survey from McKinsey suggests that, you know, the market over the next decade or so will enter the hundreds of billions of dollars. So there's a big economic prize as well, and so as you'd expect, you know, people have been thinking about this topic for a while. This was the earliest sort of vaguely related thing I could find, a radio-controlled automobile from the 1920s. No real autonomy here, but at least connection between one vehicle and another. Some other early work from with the Stanford cart here in the 60s. And again, I believe this was just remote control, but now feeding back the video feed to a remote operator, and they were sort of preparing for moon landings and things like that. One really, you know, seminal and in many respects ahead of its time pieces of work was Alvin from Honolulu in the late 80s. You know, this was actually remarkably similar to what I'll be talking about later on, in terms of how it approaches the problem. It takes a, you know, stereo pair of images and runs that through a neural network, and the neural network decides what to do. Now, very low res images, very tiny neural network. That's literally more than the neurons in this network. And it only controlled steering, no acceleration and braking or other outputs, but very impressive nonetheless. But I think it was really around the you know, mid-2000s with the DARPA Grand Challenge and then the DARPA Urban Challenge that this caught the public's imagination, right? It's sort of really impressive demonstrations that something could be done here, that these vehicles could cross the desert or navigate through towns to some degree of success, as you'll see. There are some of these that have worked and some didn't work so well. But it captured the public's imagination. It also captured the imagination of investors and the startup scene and established tech as well to some extent. And really catalyzed what I think could be called the space race of our generation, with a whole host of startups that have flourished and grown over the years. Here's just a small selection of these companies. And there has been really quite remarkable progress over the 2 decades since the Grand Challenges. And you know, if you look at, say, Waymo and Cruise, they have actual level 4 deployments, or have had in San Francisco and a few other cities in the US. And yet somehow, you know, it's not done yet. The problem's not solved. And sort of, it begs the question why, right? We've had all this time, we've thrown hundreds of billions of dollars of investment into this. And why have we not made progress? Well, you know, there's a number of factors. These are a few, right? It is just genuinely a harder problem than everyone had imagined. The complexity lies in the decision-making, not the perception. And I think there was a huge excitement with the advent of ComNets and the ImageNet and AlexNet moments in 2012-ish, where people thought, oh, wow, we've solved perception, therefore we've solved self-driving. Well, that's actually not turned out to be the case, as important as that was. Vehicle integration is interesting, right? You've got to stick sensors and compute into these vehicles, and you've got to do so in a way that is commercially viable. So it can't be too expensive. And you've also then got to bear in mind that there's a vehicle refresh cycle. So even if we had the perfect technology today, it was perfectly commercially viable, it still take 10, 20 years to get to sort of full market penetration. And then you get things like regulations, some places easier, some places harder. And of course, hype. A number of companies, I won't name any names, have obviously hyped up their products as to sell them. But looking more at the technical side of things, I think there are some really strong technical reasons why we've sort of got stuck as an industry in a rut. And so I'll briefly talk through what I'll call the traditional approach, or AB 1.0, which has been the dominant approach until very recently. And it looks something like this. You have a bunch of sensors, cameras, radar, LiDAR, GPS, others, throw whatever you can, because everything is useful and it adds value. And then you have a perception stack that will do things like lane detection, traffic light detection, car detection, free space, etc. And also localize yourself against an HD map. So, you'll pre-scan the environments you're driving in great detail. And then you localize yourself into that map and you know exactly where the lanes are and the traffic lights and the stop signs, etc. That's super useful. And then you go into planning and you work out you extrapolate where you think the other agents in the scene are going to be. And then you plan your own path and your own trajectory, which gets activated through the control system. So, what do these HD maps look like? They're sort of, LiDAR scanned point clouds plus detailed lane breakdowns, etc. And super useful if you've got them. These perception outputs, they'll typically be things like bounding boxes around the objects. And then you'll have path plans, predictions about those things, and the driving plan for yourself. So it all seems to make sense, and this is exactly how you would think as an engineer to build an autonomous driving system. But it has some drawbacks, and these have really, in practice, shown that this approach has been proven slow and expensive to scale. And so, yes, we've seen real deployments, but they're not commercially viable yet, and they're only in a few cities. So the perception stack is expensive, right? If you've got to label all of those data, all of your images, companies genuinely spend hundreds of millions of dollars just labeling data. And then you get a new sensor and you may have to do it all over again, or a new geography, you have to do it all over again. HD maps, great if you've got them, but they're expensive to build again. They're brittle. If you've got roadworks, you have to rescan them. If the road layout changes, you have to rescan it, etc. LiDAR, I've spent a huge amount of my personal career looking at depth sensing, and I love it. It's great if you've got it, but it's expensive. It's coming down in price, but it's expensive. It's hard to integrate, etc. And perhaps most overridingly, the idea of hand design rules, that you can sort of program some decision tree by hand of what you should do in every possible circumstance on the road. That's proven particularly brittle and rigid. So while all that was happening on the autonomous driving industry, simultaneously there was a bit of a revolution going on in AI, and you can't have escaped to notice many of the breakthroughs on this slide, and you could all, I'm sure, name 10 more that I could have equally thrown on this slide, of really impressive and groundbreaking advances in the broader space of artificial intelligence over the last 5-10 years. And you can even plot these on a curve and see, this is from Time, where they looked at some benchmarks data sets across a number of different tasks, and it looks like these things are accelerating. So the ability for AI to overtake human ability has been accelerating on a wide variety of these different tasks. And what's underpinning this? Well, there's several factors. I'll just quickly run through them. I do think, large training sets, data sets and benchmarks, they have allowed us to go out of, escape from toy problems, really focus on interesting real world, out in the wild problems, and also fostered competition and fast feedback cycles that have accelerated things. You've got things like games and simulation. Obviously, if you can do self-play in a game like AlphaGo, that really helps you learn how to solve this thing very, very quickly. Self-supervised learning, the breaking free of the need of manual labels, has really unlocked vast quantities of data on the web to be used at scale. Foundation models, the idea of training task-agnostic capabilities on a wide variety of tasks and a large sets of data, diverse sets of data, and then fine-tuning and prompting to achieve a particular task better. Scalable compute, the GPU, the workhorse of AI, and increasingly the GPU cloud farm of thousands of GPUs all connected in giant clusters have really allowed us to scale up these models in both model size and the amount of data we can push through these. Simultaneously, the architectures that allow us to use those GPUs effectively, particularly transformers, and the scaling laws that allow you to predict in advance, is it worth me spending $1 million training this next model because it's going to give me this much benefit? Multimodality, the idea that you can take different modalities, perhaps image and text being the most common examples today, and throw those together and get interesting mutual benefits. And things like RLHF, alignment with human goals and preferences, and the ability to then learn from in the wild data sets that are unstructured, unfiltered perhaps, and then fine-tune them and align them using techniques like this to a particular goal. And all of these, perhaps plus a couple more things like archive and the open source community that have rapidly allowed dissemination of knowledge and information, I think have been really driving the progress and the breakthroughs that we have seen. And so if I come back to these examples, I really do think that we're going to see over the next few years a very, very similar revolution in embodied AI robotics, following the same kind of patterns. Maybe we've got everything we need. Maybe there's some more breakthroughs, but similar rate of progress I expect over the next 5-10 years, let's say. And it was clear when Wayve was being founded and we were looking at the complexity of driving scenes in London that we were going to need to take a slightly different approach to what had been done before. And so we started Wayve looking at embodied at autonomous driving as an embodied AI problem, taking an AI first approach. And what does this mean? Well, it means you take that architecture diagram I showed you a few slides back, and you sort of radically simplify it. You start with a lean and flexible sensor stack. We can kind of work with whatever sensor stack one has, as long as it has certain properties, like it covers you get visibility. Then you throw the inputs of that into an end-to-end AI, a big neural network. We deliberately took a stance to avoid the use of HD mapping and localization against the map. And we train this neural network using self-supervised learning and expert human demonstration. And the output of the end-to-end AI will input is those the images or radar or LiDAR. Output is a motion plan, and then that goes up to the controller and it drives. So why is this approach interesting? Well, having these learned end-to-end policies really allows you to deal with situations you wouldn't have anticipated in advance, to align with human driving styles and preferences. The fact we don't need maps, and it's a data-driven approach, means it's relatively quick and easy to generalize to new cities and countries and driving cultures. And furthermore, you can hope to get cross geography learning, so that learning to drive in the UK can help you to drive in the US, for example. And by taking a fairly flexible approach to the sensors that we use, a vehicle-friendly approach it becomes very easy to integrate into diverse fleets. So here's a little video of our system driving around the streets of London, obviously very sped up. And this is, I think, about a 30-minute segment with no interventions across these really quite busy and challenging streets of London. Quite a different driving environment to over here, of course. We actually went and measured the density of traffic between London and San Francisco and got some stats like there are about 7 times more jaywalkers in London than you see in San Francisco, 3 times more cyclists, 2.5 times more vehicles. So it is a really challenging environment. So what you're seeing here, this is a system that's using cameras only. It's only using a sat-nav map to drive around. And this has most importantly been learned fully end-to-end. So what does that mean? It means we've told it nothing about cars or vehicles or buses or anything. We've told it nothing about lanes. We've told it nothing about traffic lights, zebra crossings, roundabouts, etc. It has learned through the examples that we've given it of experts driving these kinds of roads, how to deal with these different scenarios and how to react appropriately. And sort of zooming in on some specific examples. The top left here we have a complex intersection where you've got to negotiate between oncoming vehicles. The top right is fascinating. So we pull forward, but then we see that this vehicle wanted to come out, and we give it some space so it can turn around and zoom past us, and then off we go. Bottom left, we encounter sort of a rare case where a vehicle decides to sort of back up in our lane, and do exactly the kinds of things that a human would do. You follow a little bit, but hang back, and when it's safe, you overtake. And then another example where there's a bin that's tipped over the trash can that's tipped over into the road, and we're able to the system's able to navigate around that without any problem. And again, all of these are things that we didn't tell it how to do this other than through data. We've also been testing the generalization of our system. So we do the vast majority of our operations in London at the moment, but we periodically will go out across the UK and test in other parts of the UK, and we're now starting to deploy in the US as well. And we see generally very good driving, and it generalizes just great from London. London's a pretty diverse place already, so it's got a good coverage there, and we can generalize well to these other cities. And to also look at that thesis about the generalization across vehicles, we built an autonomous car and van, or rather retrofitted an existing car and van with our sensors and compute stack. And then we were able to train a driving policy that was able to drive both these vehicles. So we actually had the top one's the car, the bottom was the van following that car. And these are some snippets from last year where we're just driving around, and the same policy, in fact the identical same neural network and weights is driving both of these vehicles. And the last little video here I'll show of driving is when Bill Gates came to visit us last year, and Alex, our CEO, in the back there was giving him a demonstration. We took him around the central streets of London, places we had not driven on before, and and dealt with some interesting cases like that where you've got 2 vehicles spinning around each other, and I think he seems to enjoy himself through the ride. So that was a bit of an introduction to Wayve and what we've been doing and the approach we're taking. I'm going to spend the rest of the time talking through some of our research and the highlights that we've been doing here. I'm going to start by talking about language and how language can be potentially useful for driving. So if you look at a large language model such as ChatGPT today, and you ask it questions about driving, it knows quite a lot about driving. So I won't read out all of the text but you can ask it, you're driving along a road and a ball rolls out onto the road in front of you, what might happen next? And it says things like, well, you may have to brake or swerve to avoid hitting it, otherwise it could cause damage to your car, etc. But of course, it's a chat interface, and so you can probe it further, and you can do sort of counterfactuals. So, how would your answer change if you were driving next to a school? And then it says, okay, it's even more important to be extra cautious and aware of your surroundings. Children may be present, etc. And then, what if it was? Would this still be true if it was midnight? And here the risk of children being out on the road is reduced, but you still have to be careful, etc. So this is just an example, but you can go and probe these large language models, and they've codified a lot of what's known about driving. So we see several opportunities for bringing language into the mix with autonomous driving. I think the first one, which I'll talk about primarily here, is explainability, both to sort of give the user of the system and also potentially the regulator confidence that the system really understands what it's doing. It can sense everything it needs to, etc. But also some other applications such as multimodal training and reasoning, which we'll talk about briefly. So explainability, well, you're driving along, you've got your car, you've got some driving model, some language model here, and you're able to ask it questions about what it sees, about what would happen if something changed in the world, about where you're planning to drive next and why, about the rules of the road and about what it's paying attention to. And last year we launched Lingo 1, which is effectively a grounded visual question answer system for driving. Relatively simple architecture, a pre-trained large language model, and some image and video encoders, and then some LoRa fine-tuning on top of that, and turn that into a chat interface. Of course, a lot of the devil goes into the details of the data. And so we, sourced data from quite a wide variety of things, some auto-labeled perception data, some commentary data from our safety operators that would rate what they're doing as they're driving around, some simulated data, etc. And you throw this all into your fine-tuning with a little bit of RLH up on top, and you start to get some really interesting results out. So I'll just sort of play these all. And this is a live captioning system that as you drive, it would then be able to tell you what it's seeing and why it's doing what it's doing. So what's really interesting here is it's definitely able to ground the objects that it's seeing, the actions that the vehicle is taking, and explain this in a way that is concise and appropriate. We then went on to turn this into that sort of chat loop and the chat system here. So you could then start to ask the system, why are you stopped? I'm stopped because the traffic light is red. What are the top 3 hazards you're paying attention to? And then it'll say the top 3 hazards I'm paying attention to are the traffic lights, the cyclist, and the pedestrians. And why? Well, because they can impact safely and my safety and the safety of others on the road. When can you go? It can go when the light turns green. Or here's another example. What's the weather like? It's rainy. Do you drive differently when it rains? Yes, I need to be more cautious due to the rainy conditions. How come? The road might be slippery and visibility might be reduced, so I need to drive more cautiously. And when we go, I'll go once a black sedan in front of me starts moving. When will it stop raining? I cannot predict when it will stop raining. Is it true that it always rains in London? No, it is not. So So some tongue in cheek there, but hopefully this at least inspires you that this kind of interface and language-based probing of a driving system is interesting. Now, there's absolutely questions of reliable of it is this, how do you prove that this is actually accurate and representative of what's really going on in the brain of the thing. But I do think it's a very interesting first proof point on this journey. Another direction that I'm interested in for the future is sort of multimodal training, right? So I mentioned we train our driving models with expert driving demonstration data. Now, this is great and it works, but it can need quite a lot of data to really disentangle what's going on in the world and work out how to react to different situations. If we could bring a grounded language understanding into our training, we could say, take this image and describe it with, a paragraph of text about the important factors in that scene and what we need to pay attention to and why and when can we go and other things we might need to pay attention to, like traffic signs. And if you can start to then use that, I really think there's an amazing opportunity for a combined multimodal training across video and language to make it such that a paragraph of text may be worth 1,000 videos and really accelerate and help disentangle the causal factors in the driving decision-making problem much more easily. And then the other future direction I think here for language and driving is around reasoning, and it comes onto this concept of thinking fast and thinking slow. So most of the time as a human driver, you're driving around and you're probably not consciously thinking about what you're doing. Your early brain is just you've become accustomed to this. You know how to drive, you know how to steer, and that's active most of the time. But then sometimes you come across something that is more complex. You don't know how to deal with it. Your automatic brain doesn't know how to deal with it. And so then you sort of engage your more conscious thought processes, your thinking slow systems, and those sort of start to reason around this. And I think there's an interesting direction here where you do have, you can call on some higher level, slower computation and reasoning capability in a larger model occasionally to sort of help you when the thinking fast system is not working. So at present, this is just a sketch of an idea, but I do think there's something really potentially very interesting here. Okay, the next topic I want to touch on is neural replay. And this is all about taking a drive through a real world scene and turning it into a simulation. So probably many of you in the room will have heard of NRFs, neural radiance fields. This is a technique that takes multi-view images and reconstructs them into an implicit neural representation that can then be re-rendered from different viewpoints. And so you could take a driving scene like this and then layer on and then reconstruct it and then generate effectively arbitrary viewpoints within that scene at really great resolution. And so if you can do this, well, then you've got the beginnings of a simulator, right? So we can imagine, this is just a sketch, but you can imagine you reconstruct the scene and then you place your car in some initial state and you see what your driving model does. And, does it, you start it off axis and does it come back onto the sensible path, etc. And so we've been working on a version of this for a little while now, and it's coming along very nicely. So that was just a sketch. This is an actual closed loop simulator. It's a bit busy. So, the main panel is the rendered front camera from our neural replay system. You can see also the front left and front right cameras at the bottom there. And on the right side is just sort of a sort of bird's eye view, just low resolution, just to visualize what's going on in the scene. And this is all now running closed loop. So we feed those camera images that are rendered into our end-to-end neural network. That makes the decision about what driving path to follow. And then we also simulate the control system and the dynamics and physics of the scene. And then that gets you the next phase, and then you repeat that process and you have a closed loop simulator. So here's another example where we've also got some dynamic agents in the scene, and the vehicle pauses and starts to move off when the traffic when the pedestrians are clear. And here's yet another example driving down a busy street and navigating that successfully. And the nice thing is we can measure what it does in the real world and compare that what it does in simulation and get some really great metrics out of that. So on this front, I think there are some clear challenges ahead. I think the quality you saw is good, but there is clearly some artifacts, and we have some work to do, especially around the dynamic elements of the scene, which are in many respects the most important elements of the scene. If we can do that, I think there's some really interesting opportunities to take that data and use that as training data to improve the robustness of our driving models out of distribution states, for example. And I think another challenge is how you detect what's good and what's not good driving, right? Some things are kind of easy, like collisions, that they're pretty easy to detect, but giving way, are you pushing in front of another user? That's a much more complicated challenge. And so that ability to learn to detect bad driving or learn a reward function, if almost equivalently, is a very interesting topic. So I'm going to move on to the third topic today, which is world models. So to be able to drive well, you need to be able to predict the future and the different things that could happen in the future. So with this still image, it's not clear what that white car on the left is going to do. Is it going to pull out? Is it staying still? What's going on? With a video, you get a little bit more context and you get a little bit more sense here. But equally, there is a world where that white car did pull out. And so you need to be aware as a driver that that's a possibility and adapt your driving accordingly. So a world model offers you one way of doing this. It's a generative model that predicts what happens next, conditioned on your actions as the ego vehicle. And equivalently is the state transition function. And the application, there are many ways you could use such a world model. You could use it for simulation. You could use it for counterfactual experimentation. You could use it for model-based RL. And you can use it for search-based planning and many more, even representation learning, etc. There's a ton of different ways you could apply these things in practice. And there's been a bunch of great work into world models over the last few years, from Heinz Schmidhuber to Habner et al. And Jan LeCun also sees the world model as a key component of the path towards an autonomous machine intelligence. We've been looking at them in one shape or another at Wayve for a few years as well. So this is a let's see if I can get the video playing. So this is some examples from 2018 of predictions in this autoregressive world model that's dreaming the future, and then we use that as training data to learn a policy for this very relatively simple scenario of off-road driving. So this was sort of all the policy here was learned all in simulation. More recently, we've had papers such as Fiery and Mile that have looked at various aspects of the future prediction problem with real data or in simulation. But these needed either that simulator or large numbers of manual labels to be able to learn how to predict the future. And we wanted to move away from that. And so the real challenge was, can we go beyond those supervised world models and learn self-supervised or unsupervised? And there's been a lot of interest in this space from other places as well, things like NVIDIA DriveGAN, flexible diffusion modeling of long videos, video diffusion models, Align Your Latest, Magritte, Gen 2, And very recently, and after the work I'm just about to show you, of course, Sora from OpenAI, which is a super impressive piece of work. Most of these, not all, but most of these are not actual world models. They're just generative AI models. So they'll just generate the next thing, and you can't really control them. But what we did at Wayve was Gaia 1, generative AI for autonomy, which is really a world model that we can control. So I'll show you some examples from this. So to start with, this set of videos I showed you earlier in the talk and used to motivate the complexity of driving in London, these are all synthetic, generated by Gaia, so apologies for the slight misdirection. They just show the diversity and complexity of the scenes that we're able to generate. Sort of zooming into a few of these. This is just unprompted generation. Just left to its own devices, it will generate the kinds of videos that you see here. So it's imagining everything, right? It's imagining the static layout of the scenes. It's imagining the vehicles, the pedestrians, the lighting, the 3D geometry. There's nothing explicitly about the 3D geometry here encoded in this. The traffic dynamics, traffic lights, etc. And how does it work? Well, it's super simple. It's at the high level, it's just this. It's just an autoregressive next token predictor. You can prompt it if you want to with some starting images or text, or the actions, of course, that we want from the world model. Those get tokenized. You then throw that into the world model. It predicts the next token in the sequence, and then you just keep predicting the next token. And once you've got a few tokens bunched up, you can then decode those into video. And we run a diffusion model at the end just to make for the video diffusion to make them look beautiful. So once we've got this, we can do some really interesting things. So the first thing I'm showing here is predicting diverse futures. So here we prompt it with an initial few frames of image, the same starting point left and right, and we then let it go off and imagine what to do next. And it imagines one future where you drive straight and one where you went right. Here's a similar example, but a different scenario, where we start with this white car that looks like it's pulling out, and in the left side, that white car reverses out of our way and lets us go through. And in the right example, that car continues pulling out, and we slow down for it. So it really is capturing this multimodality in the set of possible. It wouldn't be a world model unless we could condition it on action. And so here's some examples where we deliberately we steer the car basically with a sinusoid pattern, different sinusoids in each of the 4 quadrants. What's fascinating here is you can actually go a bit out of distribution. So we certainly didn't drive up onto the curb in any of our training data, and yet it's able to imagine a little bit what that looks like. A similar example here with exactly the same action conditioning, but here if you look at, say, I think it's the bottom left, when it comes around again, we drive right off onto the sidewalk, and you even see things like the headlights reflecting off the wall there. And again, not in our training data, so there's clearly some level of generalization happening here, which is super fascinating. Furthermore, if you look closely at one of those panels, we see reactive behavior. So in this one, we steer directly into the oncoming traffic, and that vehicle that's coming towards us moves out of the way and tries to avoid a collision. So it's really learning something about the dynamics of the scene as well. We can condition it on language, so very simple prompts like sunny, foggy, snowy, rainy, and you get these kind of examples. Or similarly, sunlight, twilight, grey sky, night, really able to capture that wide variety of the scenes and scenarios that you see on the road. And you can combine them and say, we accelerate right and we're 15 meters behind a bus, and then it does a bit of an overtaking maneuver. So this has been fun. In terms of video generation, what we're now doing is starting to think about how do we apply this, how do we use it for driving, how do we use it simulation. And I'll just show you a couple of sneak peeks of work in progress. So the first is like controlling the agents in the scene other than the ego agent. So we can action condition the ego agent, but can we control the other agents? And so one example here is to use bounding boxes. So we say, I want a bus there. That's that green cuboid that's drawn on the left there. And I want a pedestrian and I want them right in front of the bus. And then we sort of prompt that and let it play. And we haven't run this through the video diffusion model, so it's a bit grainier than the last results you saw. But you get those pedestrians and you see them coming out. The middle one's also one where we've forced the vehicles to swerve off the road. And again, we've probably not seen that kind of thing in our training data, but we're able to now generate that and control it. And also adversarial scenarios. So, having that parked car swerve out into our way. So I think this opens up all sorts of interesting avenues for testing safety critical scenarios that aren't going to be naturally in our training set. And we're further looking at combining the best of what we saw with the neural replay with our Gaia generator and turning Gaia into a closed loop simulator. So this is also just a sneak preview there where we actually have Gaia running in a closed loop, simulating the vehicles in the road here. So many opportunities here as well. So clearly we want to leverage the advances we've seen with Gaia into our on-road driving AI and work out how to make that really impact our driving. There's more scaling up we can do. We need to bring in multi-view generation and multi-sensor generation as well. And then further pushing forward with using Gaia as a learn simulator for training and evaluation. So just in the last few minutes, I want to touch back on the topic of foundation models. And as a reminder, a foundation model is a model that can be trained on a diverse set of data that can be adapted to a wide range of downstream tasks. And you'll have seen this through papers especially in language and vision over the last few years, with just a few of the examples here, which have led to some pretty major breakthroughs. And we're of course particularly interested in what this will look like for embodied AI. And so imagine a world where you are training for multiple downstream tasks and multiple embodied AI applications trained on as diverse a set of data as you can get, on as many sensors as you can get your hand on. And trying to realize the benefits that we've seen in non-embodied applications from foundation models for these robotics applications. Now, there are some unique challenges when it comes to embodied AI and foundation models. Data perhaps being the primary one. We can't just scrape the web. If you're doing a large language model, you can go scrape the web for almost infinite text data. Similarly for images and to some extent for videos. But for robotics applications, those data sets just aren't out there, at least not in any substantial quantity. Also, the diversity of these different tasks. There's so many different types of robots that you could bring into this. And choosing what's going to add the most value and being efficient about that is challenging. The training compute is also going to be a big deal, right? This is high dimensional video data that you're often dealing with. And that's quite different again to text. So how you navigate that and how you scale these things up efficiently and without burning through billions of dollars in doing so is also a big challenge. And finally, the physical embodiment itself is a real issue. Robots are not perfect. They don't always do exactly what you ask them to, and you tell your hardware team to try and make them as perfect as possible, but there's always going to be some variation from one robot to the next, and some noise in the actuation. You've got to have, in safety critical environments, you probably can't rely on a stable, high bandwidth, low latency connection to the cloud to do your processing. You need to do it on the vehicle or on the robot. And so you need some way of distilling what could be, you know, hundreds of billions of parameters of a foundation model into something that can actually fit on a chip on the device itself. Of course, you've got the complexity then of the uncontrolled environment that you're operating in, and very importantly, the safety aspect of this, the fact that you've got to be able to operate around humans safely and be able to validate that somehow. So, despite these challenges, there's actually really quite a lot of momentum behind this in the community right now. With just again a few of the papers here. Perhaps most interestingly to me is the RTX model, which takes you know, a bunch of diverse embodiments and cross trains on all of those, and shows that each individual embodiment can now solve tasks better than had it been trained just on its own data, which I think is a really exciting development. And of course, for us at Wayve, we're very interested in these foundation models for embodied AI. Here are 3 hypotheses. We need to go out and prove them. But I do think the literature on the previous slide points to you know, positive results on these already. The idea of multitask training improving on multiple downstream tasks. So can we improve driving by training on multiple other tasks as well? Can we glean some sense of common sense understanding and reasoning, not necessarily full AGI, but something that tells us about the scene and that allows us to generalize beyond what's strictly in the training set and address those long tail scenarios. And of course, realizing some intrinsic value from those multitask capabilities. We talked about language and the explainability through that, and we talked about simulation, and eventually maybe other robots too. So with that, I will wrap up. I think Wayve has been a pioneer in the use of embodied AI for autonomous driving, and it's really exciting to see both that vision coming to fruition, and also to see others in the industry realizing that they need to jump onto this and approach the problem differently. We've seen how some of the research that we've been working on in language, neural replay, and world models are really accelerating our journey in AV 2.0. And we just touched at the end on how I think foundation models will help us unlock the full potential for intelligent robots over the coming years. So with that, I will thank you all for listening, and I will take any questions.
I have a question on Zoom. Anna, can I go ahead, Anna?
Yes, go ahead. Whoever has the microphone, go on.
So I think your presentation is very nice, very good. But I don't think that autonomous driving will succeed for all settings. I am afraid that sooner or later we're going to have, once that autonomous driving becomes more popular, we're going to have those epic congestions, right? Autonomous driving has to be safer than anything else. All your videos show very empty streets, both no cars and no people. I drive every day to work, and I never see something like that. I only see lines of cars as far as my eyes can see. And there is difficulty turning. I cannot turn right, I cannot turn left easily. And I think a car would just be standing. An autonomous car will never turn right or left. It will not pass. Now, also, I don't see many pedestrians. And I can imagine a situation in which some kids are going to be having a lot of fun stopping traffic forever, just crossing from one side to another. You see that the cars don't move. So while I think autonomous driving is great for highway driving, I don't think it will be the way to go in a city. In an empty city, yes, but in a city like New York or a big city, like I can see this not working in Mexico City, for example, or even in Paris. London, people follow the rules, but you just go to Paris and people don't follow the rules. So I don't know if you have a comment.
I think, yeah, I mean, I think that there's certainly a limit to what today's technology would do in some of the really most dense and challenging environments. I think, you know, if you were to take this to Delhi or Mumbai or somewhere like that, I think you would struggle today. I don't think London is significantly easier than Paris or New York. In fact, we've measured it, and you know, maybe that sequence doesn't convey this, but there is a lot of traffic in London too. I do think you hit on a really interesting point around the societal impact, and we're seeing this in San Francisco with some of the deployments there already. Basically, there is, you know, the Wayve and Waymo and Cruise, with their deployments there, they basically have a dial they can turn between safety and effectiveness, right? So if you just keep your car parked in the parking lot and don't move it, very, very safe, not going to cause any problems. If you dial it all the other way, it's going to get to the destination, but it's going to knock over a bunch of pedestrians on the way, right? Neither of those are particularly good outcomes. Now, what they tend to do today is to dial it back towards the safety argument, the safety end of the spectrum, which means that you get very safe driving out of it, but you do get cars stopping in the middle of the roads and blocking the roads. And so I think that's a very interesting balance. And of course, you've got to, what we've all got to work on is how do we keep the safety while increasing the effectiveness. But further is also the challenge of people jumping out in front of these cars, and we see examples of this already happening again in San Francisco. And you know, that's challenging, but that's more of a societal behavior problem. And that there are other ways to deal with that. You know, we have laws. I mean, the same argument could be made for adversarial, you know, things. You could have someone wearing a stop sign T-shirt. Well, yeah, maybe that causes the cars to stop and it causes problems. Well, you know, that's probably not like, you know, laws even today prevent you from interfering with the use of moving vehicles on the road. And so I think there is a role for legislation to play in that more as well as technology, actually. I do think you can solve the urban driving problem. That's exactly what we've been going for at Wayve, and that's exactly where we're making progress. But it is challenging. I agree.
Thank you.
Hi, Jimmy. Thanks for the presentation. One thing that I liked quite a bit about the presentation was how you use the multimodal for GIA or GIA, however you pronounce it, GIA 1. I think I felt it was quite interesting, and I'm curious to know a bit more on how do you guys plan on using it extensively for simulation. I know you tried to touch upon that and some experiments, but from what I hear, it looks like it could pretty much help in quite a lot of things in simulation if it handles physics in a realistic sense. I'd like to hear your thoughts. Thank you.
Yeah, I think that has a lot of potential there. I think the challenge you've got to overcome is that it's got to be reflective of the real world, and you've got to have confidence in that. Now, it's great at generating videos that look good, but we need to be able to take it to the next level and say, okay, we're really confident that we put this in closed loop, that the signal we get out of that is reflective of real world driving performance because we put it in the real world. And actually, I think you know, this touches on a bigger thing than just Gaia, which is just measurement in general. Measurement is super hard. I would say it's the #1 most challenging thing about in autonomous driving, because the real roads are diverse and multifaceted and never the same twice, right? You cannot repeat exactly an experiment. You can go on the same route, but it'll be different traffic, different time of day, different weather. And so getting a really strong signal out of your, out about how your driving model is doing is genuinely a very hard challenge. I do think Gaia has some strong potential here. I'm not ready to sort of lay out a full plan of how to do it yet, but it is something we're working on.
Cool, thank you.
Okay, let's take some questions in the room. I think over here we go.
I had a question regarding, so the model is pretty general, right? So how does it how does it transfer to another vehicle, for example, let's say a truck or a bus, which has a different dynamics, basically?
Yeah, so I showed you earlier the car and the van, and they are distinct, but they're less distinct than the car and a bus or a truck. I think there's a couple of considerations here. One is the scale of the vehicle and the mass of that vehicle, and therefore the momentum and the energy behind it, certainly at speed, is substantially bigger, and so it raises the safety bar. You've also got the dynamics of those vehicles and how they take corners, and you've got to think through that. And you've got, of course, the sensing and where the sensors go. We have deliberately focused on the sort of car end of the spectrum for now, mainly because we want to focus on urban, because we think that's where this technology will uniquely add value compared to highway. Autonomous trucking is great, but also mainly applicable for highway. That's where most of the value is going to be there. So we haven't looked at that end of the spectrum, but I do believe that in theory, at least, this could be same technology could apply.
Hello, and thank you for the presentation. I have two questions. First of all is the diagram you showed for the architecture of the whole driving, so of the Wayve driving, is end-to-end model, but I presume some kind of regulations already exist or will be in place shortly, and they will probably require some kind of guardrails for this kind of models. So is this architecture can actually incorporate some kind of hard rules or safeguards? And the second question is, I never seen people actually incorporating audio data to the whole pipeline, which, for example, discards all of the cases where we need to actually break the rules, for example, to make the way for fire truck or ambulance or something like this. And the only way we can actually perceive it is to actually hear it, because most of the time when we need to act on this, it's behind us and we can already hear, only can hear it.
So the audio one is actually relatively simple. You just pipe that in as an extra. We're not doing it in what I've shown you today, but we're doing it in our next generation hardware platform online now, and that has audio, and we'll just pipe that in as an additional signal. And I agree there's value there. Equally, I believe, I'm not 100% sure on this, but I believe deaf people are allowed to drive. So I think it is, you are allowed to drive even if you can't hear those signals, and you should be able to, perceive them with your eyes as well, which is why they have the lights. But I do think it's equally it is a useful signal about it. And the first one was, remind me the first question.
The safeguards and guardrails.
Oh yes, and the legislation around that. Yeah, I mean, legislation in this space is moving fast, and what tends to happen with the regulations, at least in the places we've been looking at, is they don't specify necessarily exactly what hoops you need to go through. You don't have to do exactly this perception system and exactly that, because that's been moving so fast, and as a moving target, you don't want to set something down in stone that's going to last for potentially decades in legislation. So instead, it's there are various steps you have to go through in terms of proving to them that you are taking enough care as a business in doing this. And in fact, there's a strong self-incentive to get this right too, because if you deploy an unsafe product on the road, then you know, that's obviously bad for the road, but it's also bad for the business, terrible for the business. So we are very, very self-motivated to do the right thing here.
So let me maybe conclude the questions with one more question, and then we will finish up. So your videos are very impressive, and they are, you know, showing that at least a large part of the problem is partially solved. Of course, there is still, you know, space for improvement, but in situations where there are, say, no extreme cases on the road in standard settings, it looks like the car can drive autonomously. So, well, the question arises, so when can we expect autonomous driving cars on the roads? And I guess one of the things that stop it right now is the lack of maybe proper evaluation standards that would, you know, or standardizing the notions of, say, reliability of the system, safety of the systems, and so on and so forth. So can you tell us a little bit about the work that is done towards establishing this standards and towards eventually bringing these autonomous driving systems on the roads? And it's partially links, I guess, to the previous question for you. So is there any kind of a global initiatives, say, that would establish some standards that all companies that tackle the autonomous driving problem should, you know, should obey, should look into, or how does it work right now? Can you tell us?
I mean, there certainly are there are some very well established standards when it comes to things like driver assistance products. So NCAP, for example, there's like I was reading that the other day. There's a whole range of things that they test for. They're very particular. You know, do you stop behind a vehicle? What happens when you're turning left and there's a cyclist going, you know, that way? Things like that. So there are several, and that's just one instance. There are several things like that. The sort of full autonomy space is still, as I said, quite nascent. We have a strong policy team and, you know, collaborations with groups like the Warwick Manufacturing Group in the UK, which is a university group looking at safety standards for autonomous driving, and well connected internationally. So there are efforts. There are, you know, lots of efforts going on across the world, and we're very much engaged in those as well.
Last question from the audience, if any. Okay.
I also have a question. I'm online. Can you hear me?
Maybe yes. Let's first
Yes,
take the question from the audience, because we started already.
Sure.
You can see world models paper, which combine like the concept of learned systems with some kind of planning system. You said, like earlier, I think you mentioned that planning systems can be different. Do you see some space for like classical AI systems, like search-based methods and planning in the future of autonomous?
Yeah, I mean, I certainly think you could use, you could combine, in theory at least, you could combine Gaia with a search-based planning. So you know, do some rollouts in that in its generation and see where you get to. You'd need some form of reward model cost associated with that, and then you could, you know, take the best one. So I do think that could work. It would be pretty expensive, at least today, but potentially you could do that in the latent space rather than in the, you know, the image space. That was a bit less expensive, but actually the latent space generation itself is not cheap either. So I think there's opportunities there, but you know, a lot of work to be done on efficiency.
Okay. Well, I guess last question on the Zoom.
Yes, so my question was on the verification and validation side. Since you are converting to AI for your like control is just like the perception, and then the control, the middle part is only AI. So if you're having a new feature or like having a major update in your algorithms, how that will affect your verification and validation process? Because the AI and machine learning modules are hard to trace down when you are like changing in the heart of like a model.
Yeah, I mean, I
Yeah,
think it's
that
a
was
good
my
question.
major concern. Yeah.
Yeah, I think it's a good question. I think, you know, whatever system you put out there, I do think that there's a level of verification and validation you need to do for the system as a whole. So even if you can break it down into modules that you can verify individually, the fact that they've got some complex interconnections and interplay between those systems mean that the whole system as a whole is quite a complex beast, and you need to verify that anyway. So I don't think that's changed particularly, but we are building the tools to allow us to exactly do this, because we have to, and it does make certain things more complicated. I agree, but I think the ultimate prize is that you get a system that is much better at driving and much better than it could be if you had a more traditional approach.
Let's thank the speaker again, guys.
Thank you.
Thank you so much.
I will take another one. 3, 2, 1.
Thanks so much.